All right, so this is the video for the notes on functions. Again, another lesson introducing some new concepts, some new terminology that we'll use throughout. This first chapter that I focus on, chapter 5, introduces a lot of new terms. We don't go into depth with many of them, but we do introduce a lot of things. And so here I start with the definition of what it means if something is a function. We've been talking about relationships a lot. And for example, if I look at a relationship comparing distance and time, for example, a graph like this shows me how the distance of some object changes over time. So this is a relationship. Well, certain relationships are also known as functions. A function is a specific type of relation. All right. So we've been focusing on relations, but a function is a specific type. So what makes a function a function? So a function is a specific type of relation in which every input which is the independent variable, has only one output, the dependent variable. So every input has only one output. Okay, that's what it means. If a relationship has, for every one input, there's exactly just one output coming out, then it's a function. Like all these definitions, though, the best way of understanding it is not to memorize a definition, is to use it. Although I am just going to change one thing here. I'm going to change my highlighting. I'm going to highlight output and dependent variable in blue, because I've actually been fairly consistent in all my notes so far that inputs, the x, the domain, I've been highlighting in yellow. The outputs, the range, the y values, I've been highlighting in blue. Not that it really matters too much, but here now, and you should have this. And so I have here now 9 graphs, 9 relationships. Each of these, there's no axes that are labeled, they're just graphs. What I want us to try to do here is determine which of these are functions and which are not. And remember, something is a function if every one input has one output. And what I would recommend you do is watch me work out the first 3 and then pause the video and try making an educated guess on the remaining 6. Okay, but so some of these, yes, are functions, some of them are not. They're all relationships. So let me look at this one. So is this a function? Well, if I look at this graph, I see it's discrete. I see a number of points. But for every input, that's the x, there is only one output. And I know that because there's no dots on top of each other. For example, this point right here, when that has an input, an x of 2, and an output of -1. This point right here has an input of 3 and an output of -1. That's okay. There's only, when 3 goes in, only one value comes out. All right, and so this is a function. Again, the best way of learning these things is to try a variety of them. So this is a function. Let me look at this one. This is also a function. For every input, there's only one output. For example, if I just pick a point, I don't know, right here. That looks like about 1.5. That's the input. And it looks like about 3 that comes out. I put 1.5 in, I get 3 out. Or again, x is the input, y is the output. And no matter which point I pick, there's only one output for the input. Okay, well, I'm getting tired of saying input and output. What may make things more clear, though, is if I show you this third one. This is not a function. So why is it not a function? Because if you look at these points here or these points here, they're on top of each other. Why does that matter? That matters because that means when x is 2. When x is 2, the output is either 0 or 2. There's 2 different points with the same x value. There's 2 different outputs with the same input. This is not a function. And visually you can tell because at those places, either right here or right here, I have dots on top of each other. That means this vertical line here or this vertical line here goes through more than one point. And as soon as I see that, as soon as I see it's possible for a vertical line to go through more than one point, that relationship is not a function. And that's what's kind of described up here at the top. What I just described is we call the vertical line test. If it's possible for a vertical line to go through more than one point, then it's not a function. Otherwise it is. That's it. Not saying it's easy, but that's it. So I highly recommend you pause the video and look at these 6 that remain and make an educated guess for each of them, and then we'll see in a moment if they're right. All right, hopefully you pause the video. That's it. Let's look through these fairly quickly. This next one is a function. Going back to the vertical line test, there's no point where I can draw a vertical line through more than one point here, or there's no points that are directly on top of each other. Over here, this is not a function. There are many places where one input has more than one output. For example, if I draw a vertical line right here, this is when x equals 4. So when x equals 4, the output is either 4 or negative 4. There's 2 outputs for one input, so it's not a function. Or I can see the graph goes on top of itself. This weird looking wave here is a function. It may be a bit complex, but it never is on top of itself. It passes the vertical line test, we say. Let's look right here. This is a function. However, the next one is not a function. There's a whole bunch of points all on top of each other. For example, right here, when x equals 1, y equals, well, 3, or 2, or 1, or 0, or negative 1, or 2, negative 2, or negative 3, or negative 4. All of these are outputs for a single input. Definitely not a function. And the last one here is not a function. Again, I don't know, right on the y-axis. I can see there, and there, and there. I have multiple points on top of each other, which means when x is 0, the output is a whole bunch of different possibilities. Generally, it's kind of weird. When something is not a function, it's kind of weird. You expect to put one number into something. You expect to get one number out, not 3 or 5 or an infinite number. So generally, when we're dealing with functions, they tend to be a bit simpler. But the main idea, if something is a function, we know you put one number in, you're going to get one number out. No exceptions. OK, so if something is a function, we have a new way of writing equations that we can use. And we'll use it a bit in this course, and again, lots in future courses. And what I have here is an equation written in function notation. And the way we say this first, the way we say this expression is this part here. We don't say, it doesn't mean f times x. It's not f bracket x. We say f of x. That's how we say that, f of x. So I say f of x equals 4x plus 1. So what does this f of x mean? Well, the f is the name of the equation, or the name of the function. It's a name. Right now, this is named f. That's a very boring name, f for function. But this is the name, quotes, of the function. There's a bit more I'm going to say there, but the x we say in brackets. That is the input of the function. And this right here is this side of the equation. All of this is the rule, the mathematical rule for this function. This tells you what this function does. So for this particular function, whatever number you put in, x, we multiply by 4 and add 1. And whatever that is, that's what comes out. That's the output. So another way of saying this is the input is the independent variable, usually x, and the output, in this case is f, has to do with range. I can also put that right here. That's the output, or the dependent variable. So for this particular example, x is the input, f is the output. It's also the name of it. And we say f of x. OK, so how do we use this? Well, if I look right here, this little, what I see below, f bracket 2, that we say f at 2. And I'm saying 2 is literally the input. So I'm asking you, if we replace x with 2, what do we get out? Well, let's look at my equation here. It's 4x plus 1. So in this case, it's going to be, I'll write 4x plus 1. But in this case, it's going to be 4 times 2 plus 1. 4 times 2 is 8. 8 plus 1 is 9. And so that's my output. I put a 2 in, I get a 9 out. according to this function. Function f, that's what function f does. And again, I just named it f for function. It's kind of that's kind of the convention. And so I don't have to put 2 in, I can put different numbers in. I can put negative 3.5. So if I put negative 3.5 in, what's going to come out? Let's see. So instead of 4 times x, it's 4 times negative 3.5 plus 1. Probably want to use a calculator. 4 times negative 3.5 is negative 14. Negative 14 plus 1 is negative 13. And that's my output again. Put negative 3.5 in, get negative 13 out. Or I can say, negative 3.5 has to do with the domain. It's part of the domain. Negative 13 is part of the range. Just part of it, because I can put other numbers in. So what if I ask you this? Determine x such that f equals 39. That means, if I go back to my equation, let me write down the equation again, because it's kind of gone off my screen. So f of x equals 4x plus 1. So what this question is saying is, we don't know what x is, but we know that f of x, the output, we want all of this to equal, all of that has to equal 39. So what number has to go into this equation so that 39 comes out? Right, that's my output. Well, how do we figure that out? Well, you could, I guess, do guess and check, or algebraically change f of x to 39. We know we want 39 to come out, and algebraically solve for x. And I can now solve this. I don't have to do any guess and check. I can solve this with 2 algebraic steps. And so first I want to subtract 1 from both sides. So I get 38 equals 4x. And then I want to divide both sides by 4. And so x must equal 9.5. So now I know, without doing any guessing, with a little bit of algebraic work, I know if I put in 9.5, I'm going to get out 39. And again, this here, all these parts here are using what we call function notation. And function notation is just a way of writing an equation where you are really explicit with what is the independent variable, in this case x, and we just give it a name, f. But we do that a lot with equations. When we say y, I could say y equals 4x plus 1. And it's not maybe as clear that x is the independent variable, but it's the same idea. You put in an x, you get it a y. Here you put in an x, you get it an f. I mean, it's the same sort of idea. Okay? So with that said, the last thing I want to look at is a function that is not just a random made-up function, a function that represents a relationship, in this case, between Celsius and Fahrenheit. So this equation here tells you how to convert a temperature in Celsius into Fahrenheit. And so the C we see here, that represents Celsius. That's the independent variable. Fahrenheit is the output. That's the dependent variable. So the way this equation is set up, if we know what C is, we can figure out F. And that's what that equation is telling me. This part here is saying, if we want to figure out Fahrenheit, we need to know Celsius. And how do we do it? That's what this tells you how to figure that out. So let's use this. So the first question is, determine f at 25 and explain what this answer represents. So the easiest part is probably explaining f at 25. The hardest part might be telling me clearly what this means. So first, what is f at 25? Well, that means just like before, I go back to my equation and replace c with 25. So 1.8 times 25 plus 32. And now probably go to a calculator. 1.8 times 25, all times 32. Might as well just type it all in. You get 77. So that's my output. But what does this mean? Yes, 77 is degrees Fahrenheit. But I need a bit more than that. Altogether, this equation I have here means something. And what it means is that 25 degrees Celsius is equivalent to 77 degrees Fahrenheit. Or other way around. 77 degrees Fahrenheit is the same as 25 degrees Celsius. And so I'll just write a short little statement. This means that 25 degrees Celsius is the same as 77 degrees Fahrenheit. 25 degrees being a nice warm day, not super hot, but nice and warm. And so that's what 77 degrees in Fahrenheit is. That's what that statement means. All right, so what's this? The other way around. Determine C so that f of c equals 100 and explain what your answer represents. Same idea as before. I have a little bit of calculating, and then I want to tell me what this means. This time, though, I don't know Celsius. I know f of c is 100. So how do I do this? Well, first let me write down the equation for f of c again. Okay, and so I know what that is. I know what the Fahrenheit is. I know that's 100. I'm trying to solve Celsius. And so like a similar problem just from just a few minutes ago, I can work this out by using the equation backwards by doing 2 steps of solving an equation. So in this case, I'm going to start by subtracting 32 from both sides. So I get 68 equals 1.8c. And then the last step to go from here to here is I want to divide both sides by 1.8. Because again, I only want to cancel out the 1.8 in front of the c. I want to keep the c there. And so divide both sides by 1.8. What is 68 divided by 1.8? I don't know. Go to a calculator, and you get about 37.8. It's not exact, so I'll put a little dot over my equal sign. And so what does this mean? This means that 37.8 degrees Celsius is the same as 100 degrees Fahrenheit. A very hot day. You're not going to melt, but you're going to be very, very hot and probably uncomfortable. But, you know, not unheard of. Okay, that's what that means. The last part I'm just going to leave because just for time reasons, I want to focus more not on the sketching of graphs. I want to focus more on first remembering what a function is, and then you working with this function notation. And again, this part here, which is introduced right here, function notation. Definitely probably something I expect to be new, and like all these things that are new, we're going to see them a lot on and on in future courses. But lots of new things being introduced here. So that's it. That completes this lesson. And